In this video, what I'd like to do is try and examine the relationship between the temperature of a gas and the kinetic energy of the atoms and molecules that make up this gas. And for that purpose, what I've shown over here is a cube of side L, therefore has a volume of L cube. And within this cube there is a gas, and there are, let's assume that there are a total number of n molecules of this gas within this cube. So you have this cube of volume L cube has n molecules of gas within it. Now these molecules are not still, they are randomly moving around in all possible directions. So they'll be hitting all faces of the cube. They don't really have a preference as to which face they are going to hit more than others. So on an average, they would hit each face roughly the same number of times per second. And whenever each atom or molecule collides with one of the faces, it rebounds off it. Then its momentum is changing, and so if its momentum is changing, then the rate at which this momentum change is happening is a measure of the force that one molecule or atom is exerting on that one face. And of course, since there's more than one molecule, you have to then try and calculate the effect of all molecules which are hitting that one face, whichever one we choose, and calculate the total momentum change from all the collisions that are happening from all the molecules. And the rate of change of total momentum would therefore be the force exerted on that one face. And so this is a very complicated problem to solve, because these atoms and molecules are not going around in one specific direction. They are just moving around randomly, and so there could be one going this way, rebounding off at an angle, and even the velocities of these atoms and molecules are not the same. So all that has to be accounted for. So it becomes an extremely difficult problem to solve. So, however, it becomes a lot easier if you make some very simplifying assumptions. And there are two main assumptions that you can make. One assumption is that you assume that the molecules are going only in one of three directions. So they are either moving in the x direction, y direction, or the z direction. And I call this x direction, this is y direction, and up and down is z direction. And so in other words, if you look at the right vertical face of the cube, which I will try and shade over here, then what that means is that it's only the molecules which are moving in the y direction would have any effect on the pressure exerted on the right vertical face, because the other two directions are moving parallel to this face, and they are not going to actually rebound off this wall and exert any kind of pressure on it. And the second assumption that you can make is that all atoms and molecules have a speed of v. So constant speed. All atoms and molecules have the same speed of v units, which could be anything, meters per second, centimeters per second, any unit. So with those assumptions, let's try and trace the trajectory of a molecule which is starting from the left face of the cube, and it is going to the right face of the cube, and then rebounding off and then coming here again. Now if this molecule has a mass of m and its velocity is v, then its initial momentum is mv. And once it rebounds off this face and it goes back, its final momentum is negative mv, because it's going in the completely opposite direction from where it came from. So the change of momentum of this one molecule as a result of collision with this right face of the cube is 2mv. Now what is important is the rate of change of momentum. So how frequently does it do that? How many times per second does it collide with the right face of the wall? So to answer that question, we have to remember that this molecule is starting from the left face of the wall and going in the y direction, hitting the right face and coming back. So it's covering a distance of twice the length of the cube. In other words, it's covering a distance of 2L units. And its velocity is v, so the time that it takes to have one collision with the right face is simply time is just the distance by velocity, or 2L over v. So since the momentum change, or let me just call this delta p, is 2mv, what that tells me is that the rate of change of momentum is 2mv divided by 2L over v, which gives me mv square over L. Okay, now this is the rate of change of momentum of that one molecule going from left side of the cube to the right side of the cube and back. But that's not the only molecule that's present in there, and there's a total of n of these inside this cube. Now, another assumption that you can make is that out of the n molecules inside this cube, 1/3 of them move in the y direction, 1/3 in the x direction, and 1/3 in the z direction. And so in the y direction, the number of molecules that are contributing towards a force exerted on this shaded face of the cube is just n by 3. So the total change of momentum on the right face of the cube due to collisions of these molecules with it is just the change of momentum, the rate of change of momentum of one molecule multiplied by n by 3. And so the total rate of change of momentum is simply mv square over L times n over 3. Okay. So now this rate of change of momentum from Newton's law is the force that's acting on the particle. That's acting on the face of the cube. And if we wanted to find out the pressure that's exerted on the face of the cube, all we have to do is we just have to divide this quantity by the area of that face, which is L square. And so we can therefore write down my pressure. My pressure is simply mv square over L times n over 3 divided by L square, or multiplied by 1 over L square, which, I should focus this better. So, and which gives me mv square n over 3L cube, which is the same as mv square n over 3 times the volume of the cube, which is, since L cube is the volume. So this is the pressure that's being exerted on that one face of the cube. And so let me just go ahead and take just multiply both sides by v, and so what that gives me is PV is mv square n over 3. Now we also know from gas laws that this is equal to n kT, where k is the Boltzmann constant. And so you can cancel out n, and now what you're left with is mv square is equal to 3 kT, and I'm going to write this down as mv square over 2 is 3 kT over 2. And this result is very important, because what this is telling me is that the temperature is a measure of kinetic energy of the molecules of the atoms and molecules that make up this gas. So if my temperature increases by 20%, my kinetic energy increases by 20%, and it's independent again of which gas I'm using. So I hope this was useful, and thank you for listening.